Hello, hello, and welcome to my talk. Thank you for joining my talk. Waiting until the slides come on the big screen. So, there we go. Hi. Thank you for joining so late in the evening. My name is Alex Chatzizacharias. Sure, laugh about my last name. Even in Greece, I'm half Greek. Even in Greece, they had issues with it. So I have a couple of hobbies. I like bouldering. I have a way too expensive Magic the Gathering collection. If anybody knows a nice store where I can buy cards here in Zurich, please let me know. And I really like to play video games. I play a lot of video games, and that kind of also reflects some things in my talk, as you'll see. I work at a small consultancy called J-Driven in the Netherlands. And currently I'm consulting at rootscanner.com. And that's pretty much everything I have to say about me. Are there any other gamers here, actually? Kind of. Okay, good to know. At least maybe some of my jokes will land. I'm a backend developer. I work with mostly Java, Kotlin technologies. Did some things in C# before. But a lot of people tell me that I should move to front end because I really am, always get very distracted by the next shiny thing. And they say that I would fit perfectly in the front end culture. And 1 year ago, the big shiny thing was AI, right? ChatGPT released, the revolution as we know it. So I started looking at ChatGPT, how does it work? How does Jane AI work? And there was one term that kept coming back, and that was vector databases. And that was the technology all these applications were using underwater to store their data or their embeddings. So I dove into that, made some demos, and that is what I want to show you today. Hopefully you learn something. Hopefully you'll go out and revolutionize the industry yourself. Who knows? It would be fun. Before we talk about vector databases, there's one very important part that we need to get clear, and those are vectors. Any mathematicians here? Oh, so I can't say whatever I want. Damn. Yeah, so vectors come from math. If you look it up on Wikipedia, you'll see something like that, like an arrow above a letter. And vectors are a way to encode distance and direction, pretty much. Or they're very good in that. At least that is what they used in math a lot of times. But in our context, we use them a little bit differently. Vectors are also very good at just encoding data. Vectors can have any number of dimensions. So this is a vector with 2 dimensions. This is a vector with 3 dimensions. And this is a vector with 8 dimensions. Well, if you look at this as a software engineer, you basically see an array of numbers, right? And the size of the array is the dimensionality of the vector. And you can think of it exactly like that. So if a vector has 8 dimensions, it's an array of 8 numbers, for example. So what do we do with these so-called vectors? Well, roughly 10 years ago, in 2013, there was like this research from Google where they grabbed a piece of text and they created a vector representation of that piece of text, and we call that embedding of the text. And that started becoming bigger and bigger, and people started, trying to embed more things. So eventually, images were also embedded into vectors, and right now we can embed audio, textures, 3D models, you name it. So there's like this. We're in a state of trying to vectorize and embed whatever we see. And we do that through the use of machine learning or machine learning models. So these models are trained to take certain input, text, images, or whatever, and have a vector output. And we call those techniques vectorization techniques or embedding models. There are some other names out there because in software engineering we are really good at naming things, a lot of different things, pretty much. There are a lot of vectorization techniques. The first one was Word2Vec, and GloVe came a couple of years later. But those two embedding models had a huge problem. They didn't understand context. So a word with different meanings in different contexts always had the same vector representation, which made it quite tricky to use. But a couple of years ago, the transformer revolution happened. So we had the transformer models like BERT and CLIP like 2 years ago. And these models can actually understand context. So words with different meanings in the same words with different meanings in different contexts had a different vector representation. And that really allowed, the generative AI to, go off and actually give good advice or decent advice most of the cases. So yeah, that's basically what vectors are and how we use them. Who here has no idea what a database is? I'm glad. But what is a vector database? Oh, I went all the way to the end here. Huh? Spoiler alert, spoiler alert, spoiler alert. Here we go. Okay, so what is a vector database? It's a purpose-built database. It has one purpose and one purpose only, and that is to store your vectors, and it can store and index high-dimensional vectors. So the trade-off in vector database is a little bit, okay, how high of a dimensionality do we allow in a database versus how accurate our results are going to be. And most vector databases use so-called nearest neighbor search algorithms to find the vectors that you're searching for, given a certain input. And of course, you can store all kinds of metadata associated with those objects so that you can, retrieve whatever you need to build UIs and things like that, or build applications. But yeah, so they have one purpose and one purpose only, and that is store vectors and get those vectors out as quickly as possible. So don't think after this talk, okay, I'm going to grab a vector database, I'm going to use it as a time series DB or an event store or whatever. You're going to have a bad time. If somebody, your, let's say, tech illiterate manager comes to you and asks you, okay, what is a vector database? Do we want to use this? It sounds so cool. This is the answer I gave to my tech illiterate manager. It's a database that facilitates effortless and swift semantic search on your data, with semantic being like the keyword here, right? Because if you wanted fast and effortless search, you would use Elastic or something similar, or build your own solution. But if you really are looking for semantic search on your data, think about vector databases and think about putting your data in a vector database. All right. Nowadays they are used mostly or maybe exclusively in AI applications like ChatGPT or other chatbots, stuff like that. But vector databases themselves have nothing really to do with AI. They're not inherently, built upon or for AI. So you can actually put in any vector you want in there as long as you have the vector. For example, I tried to build a Minecraft world and store the world in a vector database. Didn't work that well, but yeah, so basically you can do, if you have the numbers, you can put them in, and they will get the numbers out for you as quickly as possible. Now, when we get to databases, one thing is very important, I think personally, that is how they index your data, right? That's what you want. It has they have a lot of ways to do that, but the most popular are exact nearest neighbors or approximate nearest neighbor search. Linear search, for example, really fun to see. Because as you can imagine, doesn't necessarily scale very well if you do a linear search on your vector database. But k nearest neighbors is something a lot of developers have heard. It's pretty standard algorithm. Or shout out to Spotify for approximate nearest neighbors. Oh yeah, Hanoi. I don't know if anybody from Spotify is sitting here, but great naming. And my personal favorite, I never thought I would have a favorite algorithm, but here we are. Hierarchical navigable small worlds, and that is also what I'm going to be using and showing today. And then, of course, if you are going to do all kinds of nearest neighbor search, you need a distance metric, so something that tells you how close things are to each other. And you can basically configure whatever distance metric you want. Every vector database has different distance metrics. Euclidean distance is, the most standard, like that is basically what we know, our distance. Or similarity. Does anybody know the difference between distance and similarity? Okay, so when you're asking for distance, you're asking how how close are certain objects to each other. And when you're asking for similarity, you're asking how far apart are some objects to each other. Now, I know what you're thinking. It's exactly the same. That's what I thought. But basically, if a distance is close to 0, that means two objects are very close to each other. And if the similarity is close to 1, that means the two objects are close to each other. And then Hamming distance and Manhattan distance, things that you might have seen or might have not seen. It's not really relevant for today. All right. Very important to know is that distance calculations and indexing always happen within the same so-called vector space. And you can define your vector space by schema or by table, or by object, and many, many more. Every database has its own way of you defining, well, the vector space or your schema, as you want to call it, similar to your relational database schema, pretty much. But one very important thing about vector space is it forces you to work with the same dimensionality. So meaning that vectors with 512 dimensions will not be checked against vectors with 384 dimensions. Mathematically speaking, it's possible, but it really gives weird results, and you just kind of want to avoid it. So you always want to have the same dimensionality checked against each other. Now, me being a bit of a gamer, if I hear vector space, I take that as a challenge. So will we create a vector space for our data sets? And this is one data set where we have a data point, which is a longbow, a little bit spoiler for one of the next demos. And every planet that you see here and the texture on the planet is generated based on the vector representation of, well, that. Now, I understand this might not be the most user-friendly way of looking at your data. It's the most fun way of looking at your data. But these are basically all the data or the vectors or objects in this schema or this vector space. And basically what you see is there are clusters being formed. And what these clusters means are these are similar objects. And that is exactly what you want at your vector database. So things or objects that are similar or vector representations that are close to each other form clusters. And that means whenever you search something that is, well, similar to that object, it will find, hopefully, what you're searching for. All right. We are in a state of a gold rush when it comes to vector databases right now. I think every day new databases pop up on GitHub. I think these are the biggest right now. Could be that it's changed a little bit. For you, very interesting, I think, is which is open source, probably. So on your side, everything on your right side is open source. Pinecone and Redis is closed source. And Elastic, I'm not really sure. They're a little bit vague on their documentation because they had like this a change of terms and conditions some time ago, and since then they're like, yeah, we are open, but not really. So I'm not really sure. But yeah, VV8, Vespa, PG Vector for Postgres are all 100% open source. So if you want to get started, I would probably just grab one of those. What's really nice to see is some of these databases are so-called built-in embeddings. That means that when you supply an object, it will automatically embed or vectorize that object for you. Not all databases offer that, and that means that you have to do a call to OpenAI or Hugging Face yourself, get your vectors, and then you can store the vectors in the database. So you have to do some more manual steps. Then, of course, some of them, well, all of them want to earn money somehow. So a lot of them have managed services where you can just, you know, with a couple of clicks, have your vector databases going. It is quite expensive at the moment. I'm talking from experience. And for PG Vector, Supabase has one as a managed service. Eventually, you want to be querying these databases. Well, Python is king in world of AI, so all of them have a Python CLI. But some of them have a REST API, which you can call, like Milvus, Qdra, and VV8 and Pinecone. Some of them have a JavaScript client or a Python client. Some of them you can call through SQL, Google SQL. And Vespa you can call through YQL, which stands for Yahoo Querying Languages. Yahoo Querying Language, which I never heard about, so that was quite interesting. Yeah, so that is basically how the landscape looks right now, but it could be outdated tomorrow, so it really is going very fast. So do a little bit of research before you get started. All right, so let's get into implementing our own search. This is going to be our stack. So for persistence, I chose to use Weaviate. I have a Spring Boot application written in Kotlin, which is the superior Java GVM language. Changed my mind. And front end, I have in Unity, which is a little bit of a bad boy right now. And I don't know. I guess I like bad boys. I don't know. So why Weaviate? It's open source. It has some managed services. It's completely modular, so that's really nice. It's just all the Docker containers next to each other, so you can really plug in and plug out embedding modules. The documentation actually pretty decent, and the Java client is also pretty decent. Like the amount of what the fucks per minute was quite low when working with Weaviate. And of course, if I give a presentation like this, it's really nice that I can just run everything offline, minimize risks. And the architecture for all the demos is pretty straightforward, I think. From Unity, who doesn't know Unity? I'm sorry. Okay, Unity is a game engine. So we'll be using a game engine as our frontend. Which we'll be calling our Spring Boot app, where we have the Weaviate client library, which is going to do all kinds of GraphQL REST calls to our Docker image with Weaviate. Now, anyone that calls himself an architect here? Okay, so if you look at this through an architectural eye, you might be like, okay, cut out the middleman, just do the calls from the front end to the Docker. And my answer is, I'm a backend developer, and if I see a chance to add an abstraction layer, I'm going to take it. All right. So for today, we'll be using cosine distance as a distance metering, hierarchical navigable small worlds as our indexing algorithm, BERT, ResNet 50, and CLIP models for all kinds of vectorization we do. First, the cosine distance. This is the formula. This is the formula for the cosine similarity. Complex, I know, but what's more important is if the distance is 0, two vectors are close to each other, and if it's 2.0, that means two vectors are opposite to each other. So if you get a Java class file and a C# class file, and you put them in a database, they're gonna be close to each other, like 0.0 maybe, because C# stole everything for Java. At least that's what they say. And if you grab a JavaScript file and a Java file and you vectorize them, they're gonna be like 2.0, unless you did some really funky shit. Funky things with your Java class. All right. Hierarchical navigable small worlds are a little bit trickier to explain, so I'll try to do that a little bit different. All right. So these are eventually all the objects we want to be putting in our database. So whenever you put an object in your database, or what the indexing algorithm does is it does a proximity search and searches for the X amount of closest other objects, as you can see here, as you can hopefully see here. And then it builds, as you can see, or a neighbor graph, or a buddy graph, or a shortest path graph, or whatever you want to call it. But it builds an adjacency graph of, in our case, the 3 closest other objects. Now, eventually, what's going to happen is a data point is going to enter, and there is a random chance that that data point is going to be copied in a different layer. And in that layer, it's exactly the same thing is going to happen. So it's going to create another adjacency graph on a second layer on top of the first layer, pretty much. And then there is still a random chance, a smaller random chance, that things from the second layer are going to be duplicated into a third layer. and then there's an adjacency graph going to be created there. So you have a multi-layered graph structure with some duplication of some of your objects. And then let's say this is our vector. This is where it's gonna come. And then you're gonna to search or to find well, this object here. We have an entry point all the way on the top, and from there we're gonna search the closest vector or the closest objects to our destination, and then we're gonna use that as an entry point in our lower layer, and again use that, go to the closest object, and then again do exactly the same thing. And like that we're able to find our destination object pretty quickly. So you can traverse millions of objects within milliseconds. So that's pretty neat. So again, let's clean up a bit. As you can see, all the way in the bottom, it's a lot of steps, a lot of checks that would needed to be done. And you're basically eliminating that by creating less and less dense graphs on top of each other and finding the closest object there, and eventually going all the way to the bottom and finding the object you're searching for. All right. Who knows what I'm referring to here? You shout it. You can shout it. The Matrix. Yes. Always happy when people actually see what I'm trying to refer to with my crappy art. Okay, yeah, so the Matrix, Neo is asking for guns, lots of guns, but there is a plot hole in here. How is he going to find the guns he's actually searching for, right? So we're going to help him. We have a small CSV file with some weapons in them. We have 3 properties: the weapon name, the weapon type, and the weapon range. And then the name, for example, Excalibur sword, and the range is short. And then what VV8 is going to do for us when we put this in the database, it's going to remove the property names. You can choose not to, so that is however you want. And then it's going to basically create one string, lowercase it, and it's going to be weapon Excalibur short sword. And then through using a BERT model, is going to create the vector representation of that string, which is 384 dimensions in our case. All right. So the guns are coming. Trinity is saying, hey, you're crazy for doing this, pretty much. Neo saying, I can do this, and I'm glad he said that because the scene after this was pretty cool, to be honest. Yeah, pretty iconic. All right, so we're gonna help him find a weapon. Does somebody have a favorite weapon? Maybe a little bit of a weird question. What should we search? Any Call of Duty players here, for example? A Desert Eagle. A Desert Eagle. An AK-47. So it is a gun. Now I'm not sure I have a Desert Eagle in my data set. I don't think so. And here you can see that the range between what we found, the AK-47 and the Desert Eagle's 0.7. And I have a cutoff on 0.9, so everything above 0.9 is not being returned. So this was the closest match in our database. And that also showcased something really beautiful to me when it comes to vector databases. When you give a certain input, you can never be sure what the output is going to be. And to me, that's beautiful because you're gambling a little bit every time you do a search. But given a certain input, the output is going to be always the same, but you're not sure what's going to be. Anything else? An Uzi. Well, I need an Uzi. A Webley. We're getting smaller, but you can do things. For example, a Japanese weapon. Oh, weapon. And then you get an Odachi, which is a traditional Japanese sword. So, you know, it understands the context. Okay, Japanese, Odachi, you know, things like that. So it's pretty cool. But yeah, this is, of course, a pretty simple case. So let's make it a little bit more exciting, so to say. Anyone that plays Dungeons and Dragons here? Good. Or if you don't, just think of it as Harry Potter, like Dumbledore instead of. All right. So we have Dumbledore, which is a little bit forgetful in his old age, I guess, or a wizard in Dungeons and Dragons, which is still forgetful, and he's gonna be ambushed by a thug, and then we're gonna help the wizard to find a spell to defeat the thug. And basically, through our input is going to be transformed again through the BERT model to a certain output. All right. Okay, so this is a wizard, this is a thug, and we can do, for example, I want to cast a fireball. And then you can see produce flame, firebolt, and pyrotechnics. So we're pretty close. We didn't get the fireball that we want, but we're getting there. So let's cast a firebolt. Dead. Okay, great. But if I just do fireball, you can see that now we do get the fireball that we are actually searching for, right? So what's happening there? It's actually pretty simple because the first search was like I want to, etc., adding, a semantic sauce over my search. Well, those words are actually, being sent to the database and gonna be vectorized and then it's gonna try to match those words as well, even though you don't necessarily want to. And if you look at the data set, so these are all the spells. So I have like all the spells in Dungeons & Dragons, I put them in the database, and as you can see, it's just a lot of text, and the descriptions can get pretty, semantic. And so if a description has multiple, like if you want to do this or whatever, if you need to do or things like that, it will match those spells. So it is not a silver bullet where you can just throw in whatever you want, and it's always going to find whatever you hope to find. You really need to prepare your data a little bit. And that is also what I did here. So instead, I told the database, okay, these are all the properties I have, but I want you to only vectorize the property name and the description. And then I created a semantic description based on all the properties. So I created like a semantic paragraph that is better searchable than just, having everything vectorized differently. So anything else anybody wants to try out? Try to break my demo, maybe? An ice bolt. Is that a spell in Dungeons & Dragons? I don't know. But we have investiture of ice, icing death's frost, and chain lightning. Do you feel cold when you're struck by lightning? I don't know. So then we cast it, and then we defeat our thug. But we can make it a little bit prettier, and we'll do that in a bit. But first, that was all text, but we can do something cooler. We can also, do this exactly the same with images. Anybody that has played this game? Why? I don't know. This game is so weird to me. You're on rails and you're driving around and you're just taking pictures of Pokemon and throwing apples at them, things like that. It's so weird to me, but it was hugely popular. So I mean, there is a market for it for sure. So we're gonna recreate it. Risking the wrath of Nintendo, but I think we'll be safe. Okay, so we have our character Ash Ketchum, which really likes to flip his hat, and then is going to take a picture of what we'll see, and then hopefully find the Pokemon we are searching for. Now, our data set, so we have basically a CSV with all the numbers of the Pokemon. I have like the first, how many? 721 Pokemon. Back in my day, there were only 120 or something, so it really goes fast. Any Pokemon experts here? Okay. So if I ask which is Pokemon number 3, nobody knows. Anybody knows which this Pokemon is? Oh, yeah. So, and this is also how our icons look like. So I got this all from kaggle.com. It's an amazing website. You can download open source data sets. And basically we have a white background cartoon icon or image of every of the first 721 Pokemons. And which Pokemon is this? Ponytail, I think, right? Is that a Pokemon? Ponyta, yeah, that's it. Ponytail, what the hell? All right. All right, this is Ash, as you can clearly see. And we're walking around, and here we have a Pokemon, which is... This one is easy, huh? So if we take a picture, you can indeed see, hey, Pikachu is found. So what we're doing here is we're taking a screenshot of the camera spectrum, we're sending to the database, we're doing a similarity search, and hopefully we find the Pokemon we're searching for. So let me pause this for a second. So if you look here, the distance between the image we took and the image of Pikachu in our database was 0.23. And if we, I think Pikachu was number 25. Yeah, so this is the image, right? All right, let's, right. Now, if we walk a bit around, I think somewhere here. All right. Anybody knows this Pokemon? Beedrill, I think, yeah. And if we take him, then you get Beautifly, which, as you can see, is probably not the Pokemon you're looking at, right? So we take another image. Now it's Kabutops. So you can see it is a little bit wonky. Oh, all right. Microsoft is getting very aggressive with their... what the hell? All right. And then if we walk a bit around, I think I have maybe here somewhere here. Anybody knows this one? Yeah, the cute one, huh, Mew? And we take a picture. You're all wrong. It's Drifloon. But you can see it's a little bit wonky. So if you look at the camera, this on the bottom right, this is the camera I use to take the image of the Pokemon. And something weird is happening there, right? It's very yellow. And it's very Pikachu yellow. And I did that because, so the embedding module, how it works is, if it doesn't really understand the context of the image, which it doesn't, it's not trained to understand Pokemon, it will default to shapes and colors and things like that. So, and every single image is white. So I would always get white Pokemon back. I was a little bit frustrating, so I just put in a yellow background instead, and like that you can find yellow Pokemon quite easily, like Pikachu. But yeah, so a way to solve this would be to spend a couple million to train your own embedding module on Pokemon. Probably the best way to solve it. Or you could, use more reference images instead of just one icon, or in different styles. I could have just taken of all the Pokemon I have here, multiple screenshots from multiple angles and load them in the database, and like that it would probably be. That's actually a really good idea. Maybe I should do that. And like that, I could probably find the Pokemon I was searching for. All right. Now. We're back to our wizard, because our wizard is a little bit very forgetful. So he basically walked a circle and came back. But we're going to make this a little bit more fun for the eyes, more gamey. Did somebody play Baldur's Gate 3? It's like the best game ever, guys. Come on. So this time what we're going to do is we're going to walk around, the wizard is going to be ambushed by the thug. And then instead of immediately getting back our results from our search, we're going to grab the name of the spell that we searched for and put it back in the database, in an icon database, and trying to find an icon that matches the name of the spell that we just found or searched for. And that happens through a so-called clip model by OpenAI, or closed AI if you want to, if you like Musk, I guess. And what clip model can do is actually vectorize different different text and images and sounds into one vector space. So the BERT model, for example, could only grab text and vectorize that. The clip model can grab text and images and sound and all put them in the same vector space. So that means that you can search for images using text or for text using images, for example, which is pretty cool. All right. Our data set is looking, our icons are looking like this. So this, for example, one icon. Important to know, they're not tagged whatsoever. Everything I know is icon 13.png, and as is, I put it in the database. No tagging, no labeling or whatsoever. And as you can see, the icons are pretty good, high res. They're all the same dimensions, 512 x 512. Oh, sorry, 256 times 256. And I bought these icons on a Humble bundle like 10 years ago, and my mother said, "You're wasting your money on these things." And who's wasting their money now? 10 years later. All right. So every time I give a presentation, I have like this thing where I just need to show an explosion. So I'm going to start with that. So let's search for Fireball again. And as you can see, the icons we get match the spell name Fireball or Pyrotechnics or Fireball pretty well, I would argue, right? If you disagree, feel free to shout. And then we can cast the Fireball, and indeed, you can see. Thank you. And that is my explosion quota met for the presentation. Anybody that wants to try any other search? Can be anything. Doesn't even have to be in D&D spell. What? Nails? I need nails. Let's see what we get. I have no idea. Magic Stone. Identify and widow guess vaults of amber. Interesting. So if you cast Magic Stone, beautiful colors. Now what if I just do nails like this? Primal Savagery. I mean, could be. Which is again Fireball. So what I do, you can see it here in the logs. I basically extract the average color from the icon, so black, red, green, you name it, and the particle effect you see is based on that color. So if I do something like, wait, let me reset our poor thug. If I do like poison cloud or something. Doesn't matter, exactly. Typos don't matter. Or maybe they do. And we could do a stinking cloud, for example, and it's a different color. You all saw it. So let's see poison cloud. Let's see if we get something better. Oh no, it's the same. So it doesn't matter. It's probably the cloud thing. So what if I do like poison? What do we get then? There we go. Protection from poison, detect poison and disease, and contagion. So this should be very greeny, I think. There we go. I mean, you can really search anything. It's, a couple weeks ago at the conference, somebody asked me to search for explosive diarrhea. Sorry? Obviously, yeah. Obviously, I have no idea. I had no idea how to spell it, so I'm not gonna try it again. So, last chance. Anyone wanna see anything? A dead cat? What? A dead cat. Oh. Raise dead, speak a resurrection. It's very optimistic somehow. I don't know. So let's go with the resurrection one. Oh, nice. Death by resurrection, we say then. All right. So, if you look at this image, who recognizes this? It's Death Clock, Duncan Hill's Coffee, right? A heavy metal band. I'm a real heavy metal fan. I really love heavy metal. Anybody that hates heavy metal here? I'm really sorry for the upcoming 2 minutes or so. So there is a really big problem with heavy metal, or death metal, black metal, whatever you're going to call it. Is when you listen to the lyrics and they're grunting, you have no idea what they're saying, especially if it's a new song, right? And then you want to like, oh, what is this song? What are they saying? And then you're trying to Shazam it, and Shazam is like, I don't know what this is. So I figured I'll just make my own Shazam for just death and black metal music. How hard can it be? So what I did is I added all kinds of songs in in the database, from Beyonce, Billie Eilish, Lady Gaga, Taylor Swift. Those are not the metal bands, by the way. And then I added a song from Metallica, from Dragon Force, and from Death Clock. And Death Clock is the Duncan Hill's coffee jingle, which is like the international anthem for coffee. I don't know how you guys don't know it if you're developers, but you know. And I have a Whisper embedded in my Unity application, which is like a transcriber of music to text, made also by OpenAI. And what we're going to do is basically we're going to try and find the Death Clock jingle by just listening to what's happening. So we're going to grab the lyrics of the past 1 second or something. We're going to feed the lyrics in the database, and then hopefully we'll be able to find the song we're searching for. On your left side, you will be able to see the transcribed lyrics, so what the AI thinks is being sung right now. On the right side, you'll be able to see what the actual lyrics are. And on the top, you can see which song we have found out of the database. So who thinks we'll be able to find the song easily? Raise your hand. Who thinks there's no way we'll find the song? Who thinks it depends? I guess I am at a software conference, huh? All right, so we are transcribing the song right now. It takes a little bit of time because it's a tedious process. There we are. Beyonce, Ed Sheeran, maybe a little bit metal. Lady Gaga doesn't go that hard. Selena Gomez, Coldplay, I guess they have a guitar. Taylor Swift, against Selena Gomez. Maybe she should go into metal. Post Malone. Somehow a guitar solo is Ed Sheeran. I don't know how that's possible. Still Ed Sheeran in the guitar solo. His voice must be really, sharp. And we end with Selena Gomez. So as you can see, we didn't find the song we were searching for. And to that, I have to say, when Skynet actually rises and AI starts taking over, if we just start grunting to each other, the AI will have no idea what we're saying. It is going to be an easy war to win. I don't know what the problem was with Terminator. So thank you a lot for watching. That was it. I think I have time for maybe one question. So first come, first serve. Any questions? Yeah? Yeah? Go ahead. Oh yeah.
A couple of questions, really. First one, have you tried in your experiment searching within a multiple space? I mean, many vectors that are I don't know if you follow me.
Yeah, so different vector spaces, and that you grab
Yeah.
one input and just. I mean, you can do that, but you basically have to do multiple queries to every different space right now, because basically it's really like querying a table in a relational database. So if you want to query two different tables, or you gotta join them, that's also possible, stuff like that. So, but it's basically two separate queries that you're doing.
You did, okay, in this way. And in the list of the database you showed, Solar, Apache Solar was missing. You did it for a particular reason?
Oh
or
no, I think I
was it-
just missed it because
you
I got
did-
overwhelmed by all the databases that were out there. So Apache Solr is also one of those databases. There you go.
Yeah,
Thank you very much. I'll add it. And yeah, thank you very much. That was it. I need to make room for the next speaker. I'll be here if you have questions.